Thanks for the introduction. As already mentioned, I'm here to present Iguana, our end-to-end open source Linux-capable RISC-V SoC in 130nm CMOS. So this is the IHP tool. Unfortunately, Paul and Jannis cannot be here today. They are at home, full in tape-out stress because the design will go out tomorrow. First, I want to say some words about PULP, Parallel Ultra-Low Power. We are a research group on open source energy efficient computing architecture. The project was started in 2013, and as you can see on my shirt here, we had our 10-year celebration last month. The group is led by Luca Vanini, and it involves both ETH and University of Bologna, and it's quite a large group. We are around 100 people. Here you can see the current picture of the group. We are designing quite a lot of PULP ICs. Over the years, we have done more than 50. Usually there is one big IC every year and smaller, mostly student-driven aside of it. So there are already 10 generations of PULP ICs. You can find a full list of their capabilities, their designs, and also pictures of them on our website. So please have a look to see what they are all capable of. Education, of course, at IIS is very important, and we are also now wanting to invest a lot in the open EDA flows. We already have 4 lecture series. 3 of them are under Luca, so they are starting at bachelor levels, but also include master level, from RTL design to ASIC backend design, custom standard cells, and ASIC testing. We have 5 to 10 studentships every year. Students can start in their 5th and 6th semesters. Usually they team up in teams of 2 to 3 students, and they really go from RTL to tape out. For Iguana, we had 7 undergrad students that supported us through the design process. And of course, having an end-to-end open ASIC flow would be extremely beneficial, especially students can take it home and experiment further, and especially experiment beyond the scope of the course, so they can do their own projects in their free time and so on. Having it in the open makes it transparent, approachable, hackable, and also more fine granular. The closed tools, they are tending to have one command that does it all, and this is extremely difficult for students then to understand the technicalities and the details behind. Of course, they also are given a chance to contribute and improve the tools, but also the cell library and the flow in general. And finally, this is something that Frank would like, there is overall less bureaucracy because the students do no longer have to sign the NDAs. In the PULP group, all of our designs are open source hardware. Most of our development happens on GitHub. Some is with third parties, and that's not yet online, but we are having most of it with a permissive license. So this includes the source code, the test benches, software development kits, also virtual platforms. You can check it out. This is our GitHub page. And this really allows anyone to use it, change it, and even make products without any restrictions. Going now to Iguana, the situations and the challenges at the moment. As you just saw, open source RTL has been established, and this is really part of PULP's success. But the open synthesis and backend, they are still under development, as we already have seen today, but they are advancing very quickly. So they are established for simpler designs, but not yet for complex designs. And also, of course, we have to ask ourselves, what about fully European solutions? We have quite some strong players in Europe, but can we also create fully EU-based products out of it? Our contributions, we have created Iguana. This is a demonstrator for the IHP 13 flow. It will tape out tomorrow through Euro practice, and it will then be the first end-to-end open source ASIC, which targets to run Linux. We have created a custom pad frame allowing us complete control over the IOs. And we did in the process improvements to tool, flow, and also the open design libraries. We are building Iguana from open source industry-grade PULP IPs. This is namely the Cheshire SoC framework. And we are also including two fully digital off-chip interfaces, one for external memory, Hyperbus, and the other is a digital chip-to-chip link. This was supported by a large team of 14 people for designing Iguana. As I already said, 7 undergrad students in 4 sub-projects, 4 PhDs, and 3 staff from the design center. And of course, a lot of support from the entire PULP team. Now, let's go a bit deeper into Iguana. What is it actually? It's an SoC based around CVA6 or the Ariane core. It's a 64-bit Linux-capable Linux core, which was created at IIS and is currently maintained by Open Hardware Group. We are using AXI4 as an interconnect for the exception for some of the peripherals which are using a simpler protocol called REC-bus. It has an AXI4-based last-level cache, which can also be used as a scratchpad memory if required. A wide range of peripherals are included from VGA, JTAG, UART, SPI, I2C, and also some GPIOs, of course. It can boot standalone from SPI. It can read SD cards with the GPT partition, but it can also use or fall back to I2C EPROMs if needed. The 2 open source digital-only PHYs are again for the Hyperbus off-chip memory interface, which is connected here to the last level cache, and the other one is the chip-to-chip link, which is both a master and a slave to the internal crossbar. To go a bit further into those PHYs, we have on one side the Hyperbus, which is an automotive standard to connect off-chip RAM and flash. It only uses 11 pins, so it's nice for smaller designs that do not have too much IOs, and it achieves this by multiplex command address and data bus. The only problem with it is it requires quite a rigorous requirements on those 11 pins because it has a differential clock pair, it has the 8 parallel DDR links, and also this bidirectional strobe signal. Internally, we also need 2 programmable delay lines, which makes constraining the design quite a challenge. The digital chip-to-chip link is something that we created in-house using GPIO pads, and it's scalable. We have a configurable amount of parallel lines. For Iguana, we have 8 parallel lines, so the throughput is very limited, but it's enough to communicate with an FPGA. It uses source synchronous clocks, so it's a bit easier to constrain than Hyperbus. I already said that Iguana is based on Cheshire. Let's delve a bit deeper into that. This is our silicon-proven Linux SoC framework, which comes with a free FPGA port. So you can really start from that and easily create your Linux-capable systems. It has a parameterizable top, so you can just connect your accelerators to that and get started. It's, of course, available on our GitHub page. And we used it to already create a silicon demonstrator, which we taped last year, mainly by students, 65 nanometer load, but fully closed tool chain. Very similar SoC, so it really was the demonstrator for Iguana. We could already test it, and it's working standalone. And we already created a paper on it that was accepted last week in TCAS 2. So if you want, you can also have a look at that. Before going now into the full flow, I want to present 3 of our in-house tools that were used creating Iguana. So the first is Spender, which is a source and dependency management tool. It can also do script generation, and maybe you know Fuse SoC, so it's very similar, but it has one advantage: it can resolve project dependencies. In our group, we really have distributed our entire source code over multiples of Git repositories. In the end, it's around 100. So we need to bring all of the IPs in the proper version in, and for that we have a project manifest file and Bender that fetches all of the dependencies and the sub-dependencies in the proper version. We can then use Morty to create one single file and a single compile context, which is usually required because most of the EDA tools, especially the free ones, do not like reading in hundreds of sources. And finally, we have created SVAs, which is a simplification tool for System Verilog, as we found that there is a gap between what our System Verilog code, how complex it is, and what the tools are capable of. So SVAs does human-readable simplification of those constructs so the tools can read it in more easily. It is one of the first tools that uses the Slang parser for the Slang System Verilog parser for that purpose. Going now over to the front end, the RTL to Netlist flow. This would be the ideal flow, you know, just reading in the RTL, going through UOSIS and getting a netlist. Unfortunately, the real world is a bit more difficult, so we have Blender and Marty to collect the sources. Then we are using SVAs to simplify some of the constructs, and this is mainly parameter pre-elaboration, unification, and some system Verilog simplification. Now the code is simple enough for SV2V to be read and flattened to pure Verilog, which can then be understood by UOSIS to synthesize down. Our backend, on the other hand, is rather, let's say, standard, just open road and K layout, but we are using a custom tickle flow. And this is just based on our internal flow, which we call cockpit. We just did it because this is in line with our teaching, and so our undergrad students can directly apply all of the knowledge they gained from following the lecture series. We did not throw away the open road flow, but we rather took the tool knowledge and the technology knowledge from that. We chose to implement Iguana flat because we found in the end we had manageable turnaround times, so we did not see need for any hierarchy. In the end, most of the area, as you can see here, is occupied by CVA6. We have some part here also in the interconnect, a bit of Encore, timers and so on, and a small block for the peripherals, and of course the last level cache, because just it needs to store the data and also manage, of course, the caching state is again a bigger IP. We target 6.2 by 6.2 millimeter die size, which is roughly 40 square millimeter. To summarize, this is the overview of our current flow. Again, we already said it, Blender, sources dependency management, simulation we are doing in very later. We have pre-processing to be able to synthesize in UOSIS. We then have the backend, which gives us the GDS. Now I want to go into a bit of a second part of this talk, and I will present some of our wishes to the tools and to the flow, and also some of the difficulties we faced during the design. Let's start with the synthesis part. So here, this was a bit of a surprise for us, but the front end was more challenging than the back end in the end. And this is mainly because synthesis can be improved, especially the quality of its results. So UOSIS inherently is not timing driven, and even if you are using LS Oracle, which promises to improve the quality of results a bit, which it did, but at a very high turnaround time, or a very high increase of turnaround time, and it's only by a few %. We also saw that we have some issues with multiplication and larger arithmetic operations, and this is mainly because we, at the moment, miss a library of optimized blocks. And we also saw that standard cells and ROMs scale poorly, which was a bit difficult when implementing the boot ROM of Iguana. Also, the RTL front-end is less mature in the open domain, and this was really difficult because all of our IP is written in System Verilog, so we struggled a lot to get it in. We assessed quite a few ways of getting System Verilog code in. It's SV2V, Sherlock UHDM plugin, and of course native UOSIS System Verilog support. And in the end, none of them was sophisticated enough to read our code in, but SV2V promised the best support, so this is why we used it in the end. We found in our scouting that SLang is out there one of the best System Verilog parser. It has extremely good lexing parsing and especially elaboration functions. So far, it's just not used in tools. SVAs is one of the first tools that is actually using it, and would really hope that it's used by more people. So maybe if UOSIS and SLang can work together, it would be that we can read in the entire synthesizable subset of System Verilog without any issues. For the backend, we saw that the backend is very solid. OpenRoad has an enormous development velocity, which is extremely nice, but they have insufficient versioning. If I understand it properly, there's two versions out there, version 1 and version 2. And version 2 is from 2 years ago, something like that. And since we started the project mid-April, over 1,000 commits were created upstream, so we had to rebase recently because there were just too many bug fixes we kept ignoring. Also, some tuning is needed per technology. We included some IHP-specific changes, but to come on par with already established open PDKs in the flow, really more of those technology-specific improvements need to be done. Some of the features of OpenRoad are lacking a bit. This is mainly antenna, DRC, and DRV rule fixing. Now let's go over to a bit our dream, and also including the standard cell in the flow. So there it's super important that we take the community, or the community can take part in it. We already started this by doing 2 hackathons. We saw that undergrad students are qualified enough to work on standard cells. And of course, the more specialized cells we have, the better the quality of results. And of course, this also opens new doors for research and especially education, because students can understand the entire flow from transistor and standard cells to their design. Now, how can we make this possible? Of course, GitHub is already a nice decision, but community needs to take place in it, and moderation is of course also required, because in the end it's a technology, or it's a PDK. What is at the moment missing, or what we found is missing, is a design and evaluation environment where you just can create a cell, press a button, and later on you directly have lib and left files, so we can synthesize and implement and directly see the quality of improvements on your specific design. We saw some possibilities there already this morning, so I will not talk too much about it. Of course, in the open flow, verification plays an important role. And as we see, everybody wants to design, but nobody wants to verify. This is also true with our students, but it's extremely important. So at the moment, we just feel that there is a bit of a lack of verification. For example, logic equivalency check. There is YOSIS there that can kind of do it, but the problem is if you cannot read full system Verilog, we cannot really use it, and it's probably also not good that we have one tool that does synthesis and lag. So it would be nice to have 1 or 2 or 3 third-party open source tools, and we really need to do it because we have a very complex chain, at least for Iguana, so many steps are involved, so we need to have a lag in any way or in some form. And the tools in the chain, they need to assist the lag, so if there happens some renaming, there needs to be some change file that reflects that, otherwise lag will never converge. DRC, LVS, K-layout magic, it would be nice to have both, of course, then we have double the checks. Maybe we can find a way to describe the rules in a way that both can read them. For DFD, there's fault already mentioned today. We also didn't try it out, so we cannot give you more insight on that. And what we tried is annotated post-layout simulations with Icarus Verilog, and this was just not working out for some reason, so we also had to abandon that. I really hope that at some point we can retry it again. For the deliverables, we are targeting the fully open GDS as of tomorrow, so we are not yet so sure about the synthesis, but backend and cells should be open. The path for the open standard cells is of course clear, this is already out, but what about the SRAMs and the IO cells? As I said, it's 40 square millimeter in the 130 nanometer node. The timing, the tools or the open tools are extremely conservative, so we can only say that we should run for sure faster than 75 megahertz, but we will see once silicon is back. Our immediate next steps after tomorrow, the tape out, are to release our flow. So everybody can use a turnkey Iguana implementation on their own computers at home, start from there. As I already said, it's really built on this SoC framework, so it has a lot of possibilities to attach custom hardware on there, so it should be a very good starting point for future products. The only thing that we need to figure out is how we handle the SRAMs and the IO cells. Maybe we can use some abstract labs, so at least we have a flow that works and other people can try out. And we are targeting, of course, also a Docker, so it's super easy for people to get started. Now let me conclude this talk. We have created Iguana. It's a Linux-capable 64-bit SoC. We have the 2 off-chip interfaces, the Hyperbus and the die-to-die link. We are using industry-grade system Verilog IPs, using YOSIS synthesis, OpenRoad as a backend with our custom cockpit flow that will be released soon. The tape-out will happen tomorrow, if everything works properly, through Europractice, and we then have assessed and established the open flow also for complex designs. We gained a lot of experience in undergrad students, and I'm super happy to talk about that at some point during this workshop together with you. Iguana is not the end. We have future tape-outs planned, 2 in number, Tego and Komodo, which will extend Iguana. And there are some projects planned in terms of research, multi-core CVI6, real-time SoCs, and also in cooperation with IHB etching and reliability circuits. Thank you, and I'm now open for your questions.